Okay, so it's a quick video going through the particle model test. So I've picked out a couple of questions that you're going to need to work on, and hopefully you should be able to use these to help you with your target work as well. So first question asks you to plan an experiment that would allow a student to determine the density of an object. So if you have a look at the object, first off it is an irregular shape. So this object is irregular. So that means it's not going to be one that you can work out using the length, width and height. Okay, we're going to have to do something to calculate the total volume a different way to that. So when we're planning an experiment, we're first off going to want to think about what equation we're going to use, first. So I'm going to plan my answer to plan an experiment. So I'm going to think about, first off, what is my equation I'm going to use. Okay, so it's going to be the last thing I write, but I'm going to put my equation first. So my equation is going to be density equals mass divided by volume. And that tells me I need to find my mass and my volume. Okay. So how do I find my mass? Well, I use a balance. And how do I find my volume? I'm going to use a Eureka can. Okay, and I'm going to see how much water is displaced. And I'll go into how I would do that in a second. So when I'm starting my answer now, I'm going to just start off by saying, to find the density of the object, I would. Okay, and first off, we're going to measure the mass. And we're going to do that using a balance. Okay, once we've done that, we're then going to measure the density. So I would then measure the density. Oh, sorry, not the measure the density, I'm going to do that at the end. Measure the volume, sorry. So this is where the complicated bit of this is with the Eureka can. So I'm going to fill up the Eureka can with water. Okay, then I'm going to drop my object in it. I'm going to see how much is displaced. I want to measure how much water is displaced. Using a measuring cylinder. Okay, and when I've done that, that will tell me the volume. So you would write this out a bit better than this. Okay, I'm just going for it quickly to show you, but I've kind of written it in a bullet point sort of form. So measure the volume by filling up Eureka can water, drop the object in it, measure the displaced water, use a measuring cylinder, so that'll find the volume. And at the end, I'm just going to use the equation. Okay, density equals mass divided by volume to find density. Okay, so this is a shortened way of writing it. You could probably write a bit more detail than this, but that would get you all the points that you need. Okay, we could talk about a bit more detail about the Eureka can. You could talk about how you overfill it to start off with and let some of the water drain out, so you know it's right up at the top. And any of that's going to help with your answer to make it just a bit more solid. Okay, just making sure you're saying exactly how are you going to make sure it's as accurate as possible. Okay, now I'm going to have a look at question 3. So this asks you to describe the difference between a solid and a gas in states in terms of arrangement and movement of their particles. So when we're looking at this question, we want to go through the question and think about what is it actually asking us to do. So the key points in this are, it wants to talk about a solid and a gas in terms of their arrangement and the movement. So again, I'm going to plan this answer out, okay? I'm not seeing as much as I would like so far, planning your answers out. So it wants us to talk about arrangement and movement. Okay, and just look how quickly I'm doing this. It's really quick to just go, right, arrangement, movement, solid, gas, solid, gas. Definitely not liquid. Doesn't say liquid anywhere in there. So, arrangement of solids, I don't know, it's going to be in rows. Okay, put a bit more than that, but for now that's a good start to the plan. Right, gases, random. Okay, solids, they vibrate, don't they? And gases, they move randomly, freely, and fast. Okay, so I can barely even read that. You could probably not read that at all. I've written it really quickly. It's taken me about a minute, and it's going to really save me some time though when I'm writing my answer out. Make sure I don't waffle, make sure I talk about the things I actually need to talk about. So let's get started with the actual answer. So I'll start off by saying solids, particles, are arranged in rows, all touching, no gaps. Okay, and then you'd go on to say, however, gas particles are arranged randomly with big gaps. Okay, then I move on to movement. Okay, so solid particles only vibrate. Okay, whereas gas particles move freely and quickly. Okay, so easy 4 marks there, I think. So we should be getting absolutely all of you should be getting 4 marks on this one, because I think they're all things we know. It's just picking out what it wants you to what it wants you to say. Okay, another one we should be getting right, and there's really no excuse for this one, is the next question, which is asking what is meant by specific latent heat of vaporization. This is simple that you need to remember this. You need to just go away, learn it. Okay, write it down a million times if you need to. However it helps you to learn things, learn this definition as well as all the other definitions, which is why the rest of the definitions are your target work. We've got 2 parts to this: specific latent heat, okay, and of vaporization. So this talks about the energy needed to change state, and this talks about what state it's changing to. So the answer should be the energy needed, and that's the latent heat, to change the state of 1 kilogram, and that's the specific bit, of a liquid to a gas, and that liquid to gas is the vaporization bit. So the energy needed to change the state of 1 kilogram of a liquid to a gas. Okay, so because it's a specific, it means it needs to be for 1 kilogram, so it's saying specifically how much, and vaporization tells us it's liquid to a gas. Okay then, now we're going to have a look at a calculation involving specific latent heat. So should be straight away thinking, what's my formula? And the formula is in your formula sheet, so it was on the sheet you got, and it is energy equals mass times specific latent heat. Okay, E equals ml, m times L. So energy equals mass times latent heat. So let's go through our question. So we've got 0.018 kilograms of water, and it says specific latent heat of vaporization of water is 2.3 times 10 to the 6 joules per kilogram. And it asks us for the energy required. So just put my numbers in. I don't know my energy yet, so I'm going to put E. I know my mass is 0.018 times my specific latent heat for vaporization for water is 2.3 times 10 to the power of 6 joules per kilogram. So all I need to do is type this into my calculator, but this is where probably most of you have gone wrong. So when we're typing this in, for the mass is easy enough, 0.018 times, and watch what I'm pressing. Okay, so I'll move the calculator up a bit. So it's 2.3, I'm going to press this button here, times 10 to the power of 6. Okay, don't type times 10 and then go to the power button 6. It's just 2.3 times 10 to the power of 6. Don't need to convert that number. Don't need to do anything fancy with the standard form like you do in maths. Just type it into your calculator, press equals, and the answer is energy equals 41400 joules. So put that in my answer, 41400. Okay, last part of this question then is looking at this graph. So we've got two parts to this. Now I think one of the problems is it's section AB, and that means this line here. And section B to C, okay, so I'll circle that, is this line here. So section A to B first off, that is not changing temperature. So explain what is happening to the substance. So first off, we can see the temperature stays the same. And now, okay, and that is because energy is used to break bonds. Okay, so it's changing state. And if you're clever, you can work out it must have been a solid there and a liquid there, so it is melting. Right, B to C, the temperature is increasing. Okay, so that means the kinetic energy is increasing. And the last bit I would put on here is until it reaches boiling point. Okay, so its temperature is increasing all the way up until it reaches here, C, where it is the boiling point. Okay, moving on to, I think, question 4 now. So start with 4b. It asks about why heating a gas increases the average speed. So for this, we need that definition for temperature. So temperature is the average energy per particle, or specifically the average kinetic energy per particle. So first off, you'd say heating increases temperature. And then we'd say temperature is the kinetic energy per particle. So the average kinetic energy per particle would be better. And if kinetic energy increases, then speed increases. Okay, right, then the bottom part of this says why a mass of gaseous water at 100 degrees contains more energy than an equal mass of liquid water at 100 degrees. So basically this is saying if you have your pan of water, it's 100 degrees, and then you evaporate all of it and you have the same amount of steam at 100 degrees, why does the steam have more energy? And that's because it takes energy to boil the water to break the bonds holding it together, or holding the particles together. So it took energy to break the bonds up, so it must have more energy than it had before. Right, on to question 4D. Now I was very, very impressed with how many people not only got this right, but how many people had a really good go at it, and even if they didn't get it right, they'd got a few marks here and there for the odd bit of this, okay, because this is a really difficult question. 5-mark calculations are never easy. There's some standard form in it, there's multiple equations we've got to use, so it's not easy, but you've done really, really well to get a couple of marks on this, the vast majority of you, so well done. So, first thing we need to do is think, what have we got? So we've got a volume, we've got a density, and we've got a specific latent heat of vaporization. So we've got specific latent heat. And we want to find the energy released. So I'm not going to look at this and try and find the energy. I'm just going to look at it, because it's 5 marks. I know I'm not going to be able to answer this in one go, because it's 5 marks, and that's way too hard. Way too many marks for just one equation. So I'm just going to look and think, what have I got? What can I work out? So I've got a volume and a density, so I could work out the mass. So I'm going to do that. So I'm going to use the equation density equals mass divided by volume. Okay, I'm going to put my numbers in. So I know my density is 1000 equals 2.5 times 10, wrong way around, equals mass divided by 2.5 times 10 to the power minus 5. Okay, so I'm going to rearrange this. So because I'm dividing on this side, I'm going to times it. So I'm going to do 1000 times 2.5 times 10 to the power of minus 5. Okay, equals, and again I'll show you how I type that in on my calculator. So do 1000 times 2.5 times 10 to the power of, that button there again, but it's minus 5 equals 1/40, which is 0.025. So that is my mass, so that's kilograms. Okay, so I've got a mass now, and I've got a latent heat. So now I can use energy equals mass times specific latent heat. So I can do energy equals mass of 0.025 times 2.26 times 10 to the power of 6. Okay, so I've got my math in my calculator already. So it's 0.025 times 2.26, 0.025 times 2.26 times 10 to the power of 6 gives us 56500. Okay, so difficult equation, multiple steps to it, standard form in there, lots of things to do. But if you just look at it and think, right, I'm going to have to use my density equation because I've got density and volume. Okay, it's all about knowing your equations and being confident with them. If you know your equations like the back of your hand, then you're going to know that you've got density and volume, and you're going to have to work out your mass somewhere. And then if you know your mass and you've got a latent heat, well, just times them together because that's in your equation sheet, and we find your energy. Okay, we're on to the final question, so this is question 5. And the first part of this that I think we need to look at is this graph, okay? We did alright on the first part of this question, but this graph, when we were interpreting this graph, we'd not done a great job of it. So first of it asks us, what is the atmospheric pressure, or estimating the atmospheric pressure? So a couple of clues here. First off, it's worth 1 mark. That's telling me there's no working out needs to be done. Second part, that gives us a clue is what's up here. So it says the air was allowed to escape from the canister and the pressure was recorded every 5 minutes for 80 minutes. And think about, when's it going to get to atmospheric pressure? So that's the air, pressure of the air around you. So that's going to be when it's all gone. Okay, so the pressure is going to be, it's not going to be going down anymore. So we need to look for where it didn't go down anymore. So that's going to be here, okay, at the bottom. So atmospheric pressure is right down at the bottom here at 0.01, because it's here, and that's 0.01, 2, 3, 4, 0.5. So 0.1 megapascals. Okay, because that's 0.1, 2, 3, 4, 5. Okay, so not as difficult as a question as some of you thought that was. It's just looking at what it's actually asking you for again. It's difficult to interpret, yes, but when you know what you asked for, it makes it a lot easier. Okay, the second part, I'm going to be flipping this over a little bit, asks us to find when it was reduced to 25% of its original value. Okay, to find the maximum time they can stay underwater safely. So it says it's safe up to 25%, so what's the maximum time they can stay under? So, first off, we need to find when is it reduced to 25% of its original value. And to do that, we need to know what was its original value. So its original value was here, halfway between 2 and 2.5. So that's going to be 2.25. So we then think, right, how do we find that? So we want 25% of 2.25. Now, I don't know how you do this in maths. You might want to do 2.25 divided by 100 times by 25. I would turn the 25% into a decimal and do 2.25 times 0.25, which would give me 0.56. Okay, if I'm rounding. So I'll find 0.56. So that's 0.5, that's 0.6. It's going to be about there. Okay, and I'm going to draw my line across to where it hits the line, and then down. Okay, and if we look what the scale is on the bottom, it's 22, 4, 6, and it's halfway between 6 and 8, so it's going to be 27 minutes. Okay, so the answer is going to be 27 minutes. Okay, so that should be your whole test gone through, so you need to go and do your target work based on what you need to do from yours. You should have corrected everything in your test, so go on to do your target work now.